we have already completed the part 1 of JFET solved problems, and in part 2 we will solve two problems. The problem number 1 is based on transconductance, and the second problem is taken from GATE 1987 paper, GATE 1987 paper. Let's start with the problem number 1, in which we have to calculate the transconductance. The reverse gate voltage. The reverse gate voltage means voltage VGS of JFET when changes from 4.4 volt to 4.2 volt. The drain current, this means current ID, changes from 2.2 milliamp to 2.6 milliamp. And in this scenario we have to calculate the value of transconductance, and for this we have to first understand what is transconductance. Transconductance is represented by G subscript small m, and if you remember the hybrid pi model lecture, we discussed what is transconductance. Transconductance is equal to ratio of output current to the input voltage for constant output voltage. Very simple. In case of JFET, the transconductance is represented by GM. In some books you will find different representations, but GM is the common representation for transconductance, and in JFET it is equal to change in output current to the change in input voltage, constant output voltage. The output current in case of JFET is equal to ID. So change in output current I will represent by delta ID. The input voltage is the controlling voltage in the JFET, and it is equal to VGS, the reverse gate voltage, and the change I will represent by delta VGS. The constant output voltage must be there. Output voltage is VDS, so constant VDS should be there. So this is all for the transconductance, and using this we can easily calculate the value of transconductance in the given scenario. You can see VGS is changing from 4.4 volt to 4.2 volt. So the change delta VGS is simply equal to 4.4 volt minus 4.2 volt, which is equal to 0.2 volt. The drain current is changing from 2.2 milliamp to 2.6 milliamp. So delta ID, the change in drain current, is 2.2 milliamp minus 2.6 milliamp, and it is equal to minus 0.4 milliamp. We don't have to take this negative sign because we want the magnitude, so this negative sign is not required. So the change is equal to 0.4 milliamp. Now the transconductance is equal to 0.4 milliamp divided by 0.2 volt. When you solve this, you will have 2 milliamp per volt, or we can write 2 milliamho. We call it mho, and it is the reverse of resistance. Ohm inverse is equal to mho. This is the unit of transconductance. So this is all for the problem number 1. We will solve the problem number 2. The problem number 2 is very easy but conceptual problem. You do not require any mathematical calculations, but if you know how JFET works, then you can easily find out the correct option. In this problem, the pinch off voltage for an n-channel JFET is equal to 4 volts. This means VP is equal to 4 volts. Then pinch off occurs for VDS. This is VDS and this is VGS. Then pinch off occurs for VDS when VGS is equal to -1 volts. Very simple. VGS is equal to -1 volts. Pinch off voltage is fixed for a JFET. We already know this thing. Pinch off voltage is already given, and also the maximum drain current IDSS is given. For this pinch off voltage, when VGS is equal to -1 volts, you have to find out VDS. So this is the problem, and I think this problem is good for homework problem. As the homework problem, there are 4 options, and this problem is taken from GATE 1987 ECE paper. And once you have the correct option, post it in comment section and also try to explain the reason for it. So this is all for this lecture. In the last lecture, we saw the construction and working of N-channel enhancement type MOSFET. We saw the classification of MOSFET. We discussed what are the differences between depletion type and enhancement type MOSFETs, and the most important one, we discussed how channel is formed in case of enhancement type MOSFET. Now in this lecture, we will discuss few important terms, and we will also complete the working of enhancement type MOSFET. You can see N-channel enhancement type MOSFET on your screen. In case of N-channel enhancement type MOSFET, the body or substrate is of P-type and the 2 wells are of N-type. Metal contacts are there on both the N wells, and out of 2 terminals, one terminal will act as source and the other terminal will act as drain. The body terminal is also taken out. This is the gate terminal, and the metal contact in this case is connected in a different way. There is no direct contact between the body and the metal. There is thin layer of silicon dioxide in between. The layer is very thin in order of angstroms. You can see there is no channel between source and drain. So in case of enhancement type MOSFET, there is no channel initially, but in case of depletion type MOSFET, the channel is already there. The channel is there from the beginning. There is depletion region. We have N-type material and P-type material, so there is depletion region. You can see the width of depletion region is uniform. Now we will try to form the channel between the source and the drain, and for this purpose we have to make gate more positive as compared to the body terminal. When you make gate more positive, the positive charges will accumulate at the gate terminal and they will attract the negative charges in the body. Body is of P-type, so minority charge carriers are electrons. So electrons will be drifted towards the surface. So the region near the surface will become less P-type. Now what will happen if you go on increasing the positive potential at the gate? The uncovering of negative immobile ions will take place. The negative immobile ions near the surface will be uncovered. So the positive charges will be pushed down, and now the region near the surface, it will no longer remain P-type, it will become N-type. So this N-type and this N-type will now be joined by a channel which is of N-type. So this is how the channel is formed in case of enhancement type MOSFET. I will show you how it will look. This is the channel, and you can see the depletion region is having the uniform width. Now let us decode the name N-channel enhancement type MOSFET. You can see channel is formed between source and drain, and this channel is of N-type. Due to this reason, we have N-channel in the name. Enhancement stands for the reason there was no channel initially, but when we made the gate terminal more positive with respect to the body terminal, the channel enhanced, which was non-existent earlier. Because of this reason, we have enhancement in the name. Now we can summarize it as, on increasing voltage VGS, you can see one thing, I am representing gate to body or gate to substrate voltage as VGS. I am not using the representations like VGSS or VGB. I am not using this representation terminals in this MOSFET, but in most cases you will find only 3 terminals in the MOSFET. This is because the source terminal and the substrate or body terminal are connected internally. So the voltage VGSS or VGB we can write as VGS, which is actually gate to source voltage, because source and substrate are on the same potential. They are having the same potential. The potential difference between them is equal to 0 volt. So this is the reason we are representing gate to body voltage as VGS. Now if you increase VGS, this implies the width of channel will also increase, and at one point let's say VGS is greater than a particular voltage, and when VGS is greater than this particular voltage, the channel width is sufficient to allow significant flow of current. The current will be the drain current ID. The channel width will be sufficient if VGS is greater than this particular voltage to allow sufficient flow of current ID. We will talk about this particular voltage. This particular voltage we call as threshold voltage. You must have heard this word threshold. Threshold voltage is very important parameter in case of MOSFET. Threshold voltage we represent by V subscript T, and now I will define what is threshold voltage. The voltage that results in the significant amount of current to flow from source to drain is known as threshold voltage. The current is the drain current, and we can say when VGS is greater than threshold voltage VT, there is significant increase in the drain current ID. Now there is ID is flowing from source to drain, but in this scenario the current cannot flow. So we have to complete the circuit, and I will explain how we have to make the connections. One thing we have already covered, the source and substrate thing, we have to connect them. So I will connect the source and the substrate terminals together like this. The ground is connected in this way. Now what is the reason because of which we are connecting source and substrate together? We do not want too many biasing sources. I will write this down. We do not want too many biasing. We are connecting source and substrate. Now you can see the potential difference between source and substrate is equal to 0. So we can write VSS equal to 0 volt. They are on the same potential, and we can also represent VGSS as VGS because S and SS are on the same potential. So I think this point is clear to you. Now let's see how we have to make connections between source and drain. Current will flow through the channel, and it will flow through the channel only when the potential at D is not equal to the potential at source. So we will connect a voltage source VDS whose negative terminal is connected to the source like this, and the positive terminal is connected to the drain. Current ID will flow in this manner. Now we will make connections between source and gate, which is pretty easy. We have to make gate more positive, so I will connect the negative terminal to the source and positive terminal to the gate. So this is how you have to make the connections. This voltage here is VDS and this voltage here is VGS. Now let's try to find out voltage VGD. We want to find out effect of voltage VDS, this voltage here, on the depletion layer. I will repeat this again. We want to find out effect of voltage VDS on the depletion layer, and because of this purpose we need to find out voltage VGD. So let's use the Kirchhoff's voltage law to find out voltage VGD. Potential at this point is equal to VG. Potential at this point is equal to VD. I will start from VG, follow this path and end at VD. Let's start VG, then we have minus VGS, then we have plus VDS equal to VD, or we can write VG minus VD equal to VGS minus VDS. VG minus VD is the potential difference VGD. So in this way we have the potential difference VGD, which is equal to VGS minus VDS. Now we have to analyze three cases using the result we have obtained. In the case number one, voltage VDS is equal to 0 volt. From here you can see VGD is equal to VGS minus 0 volt, which is equal to VGS. So voltage VGD is equal to VGS. Now let's try to understand what will be the effect on the depletion region in this scenario. VGD is the potential difference between gate and drain. VGS is the potential difference between gate and source, and they are same. This means we are applying the same potential difference in this region as well as in this region. So the width of depletion region will be uniform. Because of this, width of depletion region will be uniform, or I can write uniform depletion region. This implies uniform depletion region. Now let's say the threshold voltage VT is equal to 1 volt and voltage VGS is equal to 2 volt. So VGD is also equal to 2 volt, and as VGS is larger than the threshold voltage, the channel width will be sufficient for the drain current, and the width of channel will be corresponding to the excess voltage. The excess voltage is equal to voltage VGS minus the threshold voltage. So in this case the excess voltage is equal to 2 minus 1, which is equal to 1 volt. So the channel width, let's call it CH1, is corresponding to the 1 volt. Now let's take another scenario in which VGS is equal to 3 volt and also VGD. As they are same, the depletion region will be uniform and the channel CH2 will be corresponding to 2 volt. 3 minus 1 is equal to 2 volt. In the next scenario, VGS is, let's say, equal to 4 volt and also VGD. Again the depletion region will be uniform and channel CH3 will be corresponding to 3 volt. Now if you compare CH1, CH2 and CH3, you will find CH1 will be smaller than CH2, and CH2 channel is dependent on the excess voltage, which is equal to VGS minus VT. So this is all for case number 1. Let's move to case number 2. In case number 2, VDS is not equal to 0 volt. VDS is not equal to 0 volt, but it is positive. It is greater than 0 volt. Now what will happen to the voltage VGD as compared to the case 1? VGD will now reduce because VDS is increasing. So VGD will definitely reduce, and this implies drain is becoming more positive. Drain is becoming more positive than the gate. And very interesting thing will happen. VGD is reducing. It is no longer equal to VGS, and we can say that the depletion region is no longer uniform because VGD is not same as VGS. Let's see the N channel, and according to case number 2, drain is becoming more positive, so this region is getting less positive voltage as compared to this region. So because of this, the width of channel will reduce and the width of depletion region will increase. And this is happening because there is reduction in the attraction forces for the negative charges, and due to this, width of depletion region will increase in this region. Now let's discuss the case number 3, the final case. The case number 3. In the case number 3, we will make voltage VDS equal to VGS minus VT. This is special case. VDS is equal to VGS minus VT. Now what will happen to the voltage VGD? From here you can easily find out voltage VGD is equal to VT. This is very interesting case. We are applying voltage VGS. If you see the MOSFET, we are applying voltage VGS to overcome the threshold voltage VT, but when VDS is equal to VGS minus VT, then VGD will become VT. It's like applying VT in the opposite direction. Let's try to understand this by the help of one example. Let's say there is one wall, there is this wall, and you want to climb this wall. This wall is VT, and you are using another wall for this purpose, and this wall here is VGS. You are using this wall to climb VT, but when VDS is equal to VGS minus VT, in that scenario, when you climb this wall, when you climb VT, you will again find the same wall VT, and this is due to VDS equal to VGS minus VT. So what will happen? As we are unable to overcome the threshold voltage VT, the channel will become very narrow, the width will be almost 0. But one important thing you have to keep in your mind, this will happen only near the drain. This will happen only near the drain. The channel will become extremely narrow. This will be the increased depletion region. This is how it will look. Okay, and the channel will not completely vanish, because in that case current ID will become 0, which is not possible. This condition is known as pinch off. This condition is known as pinch off, and the voltage VDS is known as VD saturation. VD saturation we are calling it because when you increase VDS more than this, current ID will remain constant. So we call this voltage VD saturation, and we represent it by V subscript DS subscript SAT. So this is all for this lecture. See you in the next one.